This is video number 2 of the Haber process. In video number 1, we gave an introduction to it. The process Haber process is and we talked about nitrogen reacting with hydrogen to make ammonia. This is the Haber process. The Haber process is about making ammonia. Okay, ammonia is used as the raw material for making fertilizer, amongst other things. It's not fertilizer, it's the raw material for making fertilizer. Now, this is not a straightforward reaction. We learned that in the first video. It is a reversible reaction. If we look at this arrow here, it's a half arrow that way and a half arrow that way. The nitrogen and hydrogen react with themselves to make ammonia, but that's not where it ends. The ammonia can react with itself to make nitrogen and hydrogen, thus undoing the process. Now, in this video, we're going to look at how chemists can ensure we get as much nitrogen and hydrogen making ammonia as possible, and try and limit the backward reaction. So I will call the nitrogen hydrogen making ammonia the forward reaction, that's the forward reaction that way, and we'll call the ammonia reacting with itself to make nitrogen hydrogen the backward reaction. Okay, so when I use those terms, forward reaction and backward reaction, I mean going forwards to make ammonia, going backwards to make the nitrogen and hydrogen. Right, so how can we shift this balance, if you like? Then I always like to think of this as a seesaw. Now, when my two daughters sit on the seesaw, it never balances out because my older daughter's heavier because she's older, and so that weighs it down. My younger daughter sits up in the air. Now, my younger daughter often gets the hump with that because she doesn't like being sort of marooned in the air, so I have to change the equilibrium to ensure my daughter's happiness. I do this by standing on my younger daughter's side, and the seesaw comes down. So what can chemists do to affect the balance of this seesaw in this reaction? Well, they can change two things. Essentially, they can change the temperature and the pressure, and we'll talk about those one at a time. Temperature first. Now, to understand this, you have to remember that reactions can be either exothermic or endothermic. So an exothermic reaction, just to remind you of the definition, exothermic reaction gives out heat energy. And an endothermic reaction takes in heat energy. Okay, now they're the definitions, and I think a lot of people understand those because ex is exit and therm is heat, so exit heat, enter en, and therm enter heat, takes in heat energy. So a lot of people get these definitions, but then they get confused about which one gets hot and which one gets cold. Taking in heat energy, for example, sometimes people think that gets hot. Well, that's not true. That's not true because the thermometer is on the outside of the reaction. So the thermometer is measuring the surroundings of the reaction. So if the reaction takes in energy, it's taking energy from the thermometer in, so that one gets cold. Easier to spot, giving out energy. A bonfire gives out energy and that makes us hot. So we need to remember which one makes us hot and which one makes us cold. Now, in a reversible reaction, one reaction will be exothermic and one reaction will be endothermic. Now, you can't tell just by looking at the equation, you are told this. Now, in the Haber process, this forward reaction happens to be exothermic. So that's the one that gets hot. And the backward reaction happens to be endothermic, but that's not the case in all reversible reactions. You will be told in the question. If it's a different reversible reaction, you'll be told which way is the exothermic and which way is the endothermic. So you need to look at that. Okay, so that's important to start with. Now, the second thing you need to know is a scientist called Atelier came up with this. Atelier said, he came up with a principle. His principle was that equilibrium reactions, reversible reactions like this, will move to oppose a change enforced on them. So in other words, if we make this reaction hot, it will want to make itself cold. And that's how we shift the balance point, by understanding which is the exothermic and which is the endothermic. Let's read through this and have a go. Dynamic equilibrium reactions move to oppose the change in conditions, i.e. if you heat it up, it will move in the if we're going to heat up, it's going to move in the endothermic direction. Because endothermic makes it cold. So if we heat it up, it's going to move in the endothermic direction. It's much like turning the heat up in the room. You take your jumper off to cool yourself down. Okay, reactions are just the same. So if we add heat to it, it tries to cool itself down. Does increasing the temperature increase or decrease the yield of ammonia? And give a reason for this. So increasing the temperature is making it hot, therefore it's going to drive the backward reaction, it's going to decrease the yield. Okay, So what we're going to write about that? We're going to say, first off, the Ford reaction is exothermic. That's the first thing we need to say. The Ford reaction is exothermic. That makes it hot. Okay? And we're increasing the temperature here. So the next thing we need to say is equilibrium reactions. That's Le Chatelier. Equilibrium reactions, Le Chatelier said, they move to oppose any change. So if we heat up this reaction, this is a reversible reaction. If we heat it up, okay, we are not going to favour the exothermic reaction. We are going to favour the endothermic reaction because the reaction is going to move to oppose the change. It's going to move in the direction that makes it colder. Equilibrium reactions move to oppose any change. So let's just say the last bit here. This favours the endothermic reaction. Okay. In this case, the backward reaction. Hence, the decrease in yield of ammonia. Ammonia, of course, was the NH3. So, increasing the temperature reduces the yield of ammonia, and that's what we've said in this box here. So the second way we can change the equilibrium position of a reversible reaction is to change the pressure. And this works if our reactants and products are gases. We can change the pressure, and that shifts the equilibrium. What we have to do to understand this, we have to be able to count the gas molecules. Okay, now students find this hard because they forget the correct definition of molecules. So we need to count the gas molecules on the left of the equation and on the right of the equation. So here we have one nitrogen molecule. Okay, so if we had a box on the left-hand side of the equation here, it's going to have one nitrogen molecule in it there. Okay, and we've got 3 hydrogen molecules. So I could have 3 hydrogen molecules. There's 1, there's 2, and there's 3. So in this box on the left of the equation, I've got 1, 2, 3, 4 gas molecules. Now, when I often ask this question to a class, some hands will go up and somebody will say 8. Now, what they're doing is they've misunderstood the definition of the word molecule. The molecule is the covalently bonded particle made of 2 nitrogen atoms. Okay, in that case, or the covalently bonded particles made of 2 hydrogen atoms. There are 8 atoms, but that's not the question that's important to ask to understand how pressure affects an equilibrium. And the question we have to ask is, how many molecules are there? So there's 1, 2, 3, 4 molecules on the left-hand side of that arrow. Okay. Now on the right-hand side of this arrow, I've got 2 ammonia molecules. Again, I asked the question in class and somebody put that hand up and say 8. And well, there are 8 atoms there. Of course there are 8 atoms. There's 8 atoms on the left, there's going to be 8 atoms on the right. The equation is balanced. But that's not the question we're asking. We're asking how many ammonia molecules there are. So an ammonia molecule is made of 1 nitrogen and 3 hydrogen atoms. And there's 1 ammonia molecule. And here happens to be another ammonia molecule. So on the right-hand side of the equation, we have got 2 molecules. So how many gas molecules on the left? Answer 4. How many gas molecules on the right? Answer 2. Which side has the least gas molecules? That's the easiest question I've ever asked, I think. The right-hand side. The right-hand side has less gas molecules. 2 molecules, 4 molecules. So if you increase the pressure, does the equilibrium shift to the left, the N2 and 3H2 side, or the 2NH3 side? Now remember, equilibrium reactions move to oppose change. So if we increase the pressure, the system is going to try and reduce the pressure on itself. Now pressure is caused from gas molecules bouncing off the walls. So wherever there's less molecules, there's going to be less pressure because there's less molecules to bounce off the wall. So if we increase the pressure, the system is going to shift to the right, the 2NH3 side, and that's what we want to make. We want to make ammonia. Okay, so it's going to go to the 2NH3 side. So does increasing the pressure increase or decrease the yield of ammonia? Answer, increase. Okay, it increases the yield. Why? The left-hand side, I'm just going to write LHS just for speed here. The left-hand side has 4 gas molecules. Let's just move that down a little bit. The right-hand side has 2 gas molecules. So we need to say this again. The equilibrium moves to oppose change. Key fact. So the equilibrium will move to the right, moves to the right in this case. If we increase the pressure, it moves to the right with the aim of lowering the pressure, to lower the pressure. There's less molecules on the right, less molecules to bounce off the walls. So moving to the right lowers the pressure as there are less gas molecules. Okay, what that does, this makes more NH3, more ammonia. Okay, last question. So in reality, and if you go back to the video 1, in reality a medium temperature of 450 degrees C and a high pressure of 200 atmospheres is used. Why can we explain these conditions? Well, we heard increasing the temperature reduced the yield. So why have we heated it to 450 degrees? Well, the answer is because increasing temperature speeds up the rate of reaction. Now we could go much, much hotter, but that would decrease the yield too much. So 450 degrees C is a compromise temperature. It's a compromised temperature, and that's really important. Okay, increasing the temperature decreases the yield, but increases the rate. A compromise is used. Compromise, keyword, a compromise is used. A medium temperature is used. 200 atmospheres is a very high pressure. High pressure, okay, both increases the rate and increases the yield. Okay, that's the highest pressure they can use safely. So they do that. And that's the Haber process.